So we would like to find a potential for the conservative vector field with components y plus cosine x, comma e to the y plus x. And let's recall a few things about conservative vector field. So first of all, a conservative vector field is the gradient of a scalar function. And of course, one might wonder why we call them conservative and we don't just call them gradients. And the answer to that is actually pretty simple because we want to actually focus on the vector field itself, not the function that generates it, or rather the properties of the vector field itself. In some cases, might not even be immediate to see what the function is. And for example, that's what we do in this particular problem. We find a potential for the given vector field. So in any case, let's discuss this a little further. So the gradient, at least in the case of two dimensions, will look like phi sub x comma phi sub y. And if we call the first component, if we call it P, and the second component, if we call it Q, then we see right away that Clairaut's theorem that reads f sub x and then sub y, so these subscripts, of course, denote differentiation, is the same thing as f sub y and then sub x, which really means that P sub y is equal to Q sub x. And this, of course, by Clairaut's theorem, a necessary condition for a vector field to be conservative. And it also shows you how unusual conservative vector fields are. I mean, if you randomly choose a vector field, it's very unlikely that it's going to be conservative. Of course, one might ask if this condition is also sufficient. And the answer is that, in general, no. It is sufficient over nice sets like rectangles. R square, meaning the whole plane, can be considered as an infinite rectangle, and it's true for that, which means that in the case of our vector field, if we call the first component P and the second Q, we can see right away that P sub y is equal to 1 and Q sub x is also equal to 1, which means that it's going to be conservative. Of course, we know that because it's part of the statement. Now the question is, how do we find a potential? And again, I'm saying a potential because if you have one potential, then you can add any constant to it and you will get another potential. So a potential is by no means unique. And the idea is pretty simple. So since, let's say, the first component is the derivative of a potential with respect to x, then we should be able to recover, at least partially, as we're going to see, the potential by integrating with respect to x. You might call this partial integration, even though I'm not sure that this kind of terminology is so common. But in any case, we can take y plus cosine x and integrate with respect to x, and that will give us yx plus sine x. And here is the interesting part now. Normally, when we do integrals like that in one variable, we put a plus c that reflects the flexibility that we have for the antiderivative. But here, it's a partial antidifferentiation in some sense. It's partial integration, if you like, and it's not just constants that disappear upon differentiation. It's also functions of y, since we're integrating with respect to x. So we can certainly allow ourselves to have a full function of y, and the derivative with respect to x would be the correct one. But more importantly, this flexibility of choosing this function of y will ensure that not only the partial derivative with respect to x coincides with the first component, but also the partial derivative with respect to y coincides with the second component, and that's what will help us pin down this function. So we write that the partial derivative with respect to y of the initial guess that we have made based on our integration for the potential should coincide with the second component. So it should be to the y plus x. Well, we take the derivative with respect to y, and that gives us x plus g prime of y. That should be equal to e to the y plus x. And now we can see a nice cancellation of everything that involves just x, and we're left with an expression of y. And this, of course, something that has to happen if our vector field is to be conservative. This implies, of course, right away that g of y is equal to e to the y. And that determines that our potential, or a potential for our vector field, will be given by yx plus sine x plus e to the y. And that's the potential. And that's it. Thanks for watching.